Now I'll combine the small signal picture of the voltage controlled voltage source or the source follower which we have synthesized with a suitable biasing arrangement to complete the circuit. Okay. Now the incremental picture looks like this. Drain, gate and source of the transistor. This is of course VGS and the load is connected there. Now we know from our experience with the common source amplifier that when we set up the biasing arrangement for the transistor, there could be some extra components. For instance, to bias the gate, there could be some resistors and so on. Okay, so that may also happen. Okay, then we'll have to put a constraint on their values so that we still have the result that we wish to have. Okay. Now, what is a suitable way of biasing the MOS transistor? There are first of all 4 different ways: the drain feedback bias, the source feedback bias, and sensing at the drain feeding back to the source, and sensing at the source feeding back to the gate. Out of these 4, the last 2 of them, sensing at the drain feeding back to the source or sensing at the source feeding back to the gate, involve yet another inverting amplifier stage. Okay, I illustrated these circuits with an op amp, but there is some extra amplification stage that is required so that you have the inverting gain from drain to source or source to gate. Okay, now that for now it is just too complicated, because after all we are looking at a single transistor circuit and we don't want just for biasing to use another op amp. Okay, we prefer not to use such complicated biasing arrangements in this case. The remaining 2 are drain feedback, where we have a current source connected to the drain and drain is also connected to the gate for feedback, and source feedback, where a current source is connected to the source terminal and the gate is connected to a fixed voltage. So how would you choose between the 2? You choose based on which is more convenient. The first thing you notice is that in this circuit here, in our circuit, the source terminal is not connected to ground, whereas in the common source amplifier it was connected to ground. So if we use this first circuit, the drain feedback circuit, the source is connected to ground, or it could be connected to a fixed voltage, but in the incremental picture this will be ground. Okay, so somehow if we use this, it has to be connected to ground for the biasing arrangement, but it has to be lifted from ground for small signal incremental purposes. Okay, that can be done using an inductor and so on, but it is again cumbersome. Whereas this second circuit, the way it is, the source is anyway not connected to ground. Okay, which is how we want it here. In the incremental picture, the current source becomes an open circuit and the source is floating as it is, right? That's exactly what we want here. So this is the most convenient circuit for use with the source follower or the common drain amplifier. Okay, so that's what we are going to use. Now, it is possible to combine any incremental picture with any biasing circuit using a proper combination of capacitors and inductors. But some of them will become too cumbersome, because our goal is not just to realize circuits that work, but also do them in the most efficient way possible. Okay, now it doesn't mean there is always just one unique choice, but in this case at least the second one appears more convenient, and let's use that one. Okay. So let me redraw the biasing part. Let's say it's biased at a current I0. In the drain, it's connected to the incremental ground here, but it cannot be connected to ground over there, because then we cannot have the transistor in saturation. Okay, the drain voltage has to be above the source voltage. So let's say that it's connected to some fixed voltage, and that is nothing but the supply voltage VDD. Okay, remember this is what we did when we came up with the biasing circuit in any case. The gate has to be connected to a fixed voltage, and as before, we don't want to use yet another DC source for biasing the gate. So what do? We take the drain voltage, divide it appropriately using a resistive divider, and bias the gate. And this is a perfectly acceptable arrangement because the gate draws no current. So the values of R1 and R2 can be arbitrarily set. If you look at this voltage, it will just be R2 by R1 plus R2 times VDD, whether you connect the gate or not, because the gate doesn't draw any current. Okay. So now we have a transistor that's biased at a current I0 and it's in saturation and so on. Okay. Now we have to somehow connect the input source to it and the load to it. Now we have done this so many times, it's quite easy. I'm sure you can do this with your eyes closed. We have the signal source Vi. Now how do I connect it to this? Again, I will use the constraint that I've been using for all the circuits so far. The minimum signal frequency is greater than 0. That is, we are not interested in a DC signal. It has some minimum frequency. It could be 1 kilohertz, it could be 1 hertz, it could be 1 megahertz, whatever it is, but it's not 0. Okay. In that case, we can use capacitive coupling to combine the DC value obtained from the voltage divider with the signal obtained from the source. So I do this, and this picture now must look very familiar to you. Okay. And how do I connect the load? The load must appear between the source terminal and the ground. So I AC couple it. Okay. Because first of all, this is not just a resistance, as I have repeatedly emphasized, it's just a representation of what comes later. But even if it were just a resistance, if you connect it there, what happens is there will be some voltage here and some current drawn by this, and the current through the MOS transistor will not be just I0, it will be I0 plus the current through the resistor. Okay, so the bias will be disturbed, so we don't want that. So the correct way to connect the load resistance RL is by AC coupling through a capacitor C2. Okay, so that's all that's there to it. Now we have biased the transistor, we have connected the input, and we have also taken the output. Okay, so this circuit is the complete diagram of the source follower or the common drain amplifier, or a voltage controlled voltage source with a gain of approximately 1. Now you have to choose the current I0 such that GMRL is much greater than 1. Okay, the output of course is here. It's quite common to show this as one of the elementary stages using a MOS transistor. You show the common source amplifier and then the common drain amplifier and so on. But we prefer to think of it as a feedback arrangement, because feedback is essential to making the gain of this stage V0 by Vi close to 1. Now the important thing here is this is quite different from a common source amplifier whose gain is minus GMRL. You can always set RL equals 1 by GM and make this equal to minus 1. But what happens is, if the value of RL changes, if you choose a different load resistance, the gain will change. Similarly, with temperature, GM will change and the gain will change. Okay. Whereas in our source follower or the common drain amplifier, V0 by Vi is really GMRL by 1 plus GMRL, and we choose GMRL to be much more than 1. Now clearly you can see that if RL changes a little bit, as long as you satisfy this condition, the gain will be 1. Okay, the gain will be close to 1. The exact value of RL doesn't matter. Okay, if GMRL is much more than 1, in the denominator 1 is negligible compared to GMRL, and this gain will be close to 1. Also, if because of temperature and so on, if GM changes a little bit, again nothing happens, because the GMRL product will still be much more than 1 and the gain will be close to 1. So there is a qualitative difference between the common source amplifier, which has no feedback, and a common drain amplifier which has feedback. The circuit with feedback, the common drain amplifier, is much less sensitive to the load and source conditions as well as the operating point and the small signal parameters of the MOS transistor. Okay, so this is a very important distinction. Here I have put down the small signal picture of the source follower that we originally synthesized and the complete circuit diagram that we got by trying to combine this with a suitable biasing arrangement. Now what is the difference between this and this? This circuit is not complete because R1 and R2 are missing from the picture. Okay. R1 parallel R2 must appear here. they go from gate to VDD, which is the same as small signal ground, and also they go from gate to ground. Okay, so R1 parallel R2 appears between gate and ground. So that's all that's there to it. So this is now the complete small signal picture corresponding to this circuit, with the assumption that C1 and C2 are large enough so that they are shorts. Okay, they are very large. That's the assumption. Okay. So what is the essential difference in functionality? The only thing is there is now a voltage division between the actual input source Vi and the gate terminal of the MOS transistor. Okay, we wanted the input resistance of the source follower, that is here wherever you connect the source, right? Looking in there, we wanted that to be infinite. Now we know that it's not infinite. What is it? I'm not going to evaluate this separately. It's very easy to see that it is equal to R1 parallel R2. Okay, so now the gate voltage is not exactly the same as Vi. The gate voltage will be Vi times R1 parallel R2 divided by Rs plus R1 parallel R2. In fact, we had got exactly the same type of expression with the common source amplifier as well when we use this type of biasing, the source feedback biasing. But this situation is quite easy to take care of. You have to make sure that both R1 and R2 are much greater than Rs. If you do that, then this ratio will be very close to 1 and the gate voltage will be approximately equal to the input voltage. Okay. So that's the only thing that has come about because of the biasing arrangement. Everything else looks exactly like this, right? RL is connected to the source and it will be connected to the source if C2 is sufficiently large. Okay. That's fine. So this completes the circuit of the source follower or the common drain amplifier, and it's quite a useful circuit. It's used in a lot of places. For instance, the microphone into which I am speaking, many of them, the microphone itself will have a very high output resistance or a very high value of Rs, and it won't be able to drive the following circuit. So it's very common to use a source follower immediately following the microphone, so that you have the same signal here as that comes out of the microphone, but the output resistance is much smaller. So this can drive a much heavier load and consequently not attenuate the signal from the microphone. Okay, so it's a very widely used circuit and it's one of the basic amplifier topologies. Okay, the common source amplifier is the other one.